So this has been broken up into three regions, region 1, 2, and 3. And we're going to solve the Schrödinger equation in each one of these regions. And I'm going to give you a little Easter egg here for your exam. I'm going to go through the ansatz method and show how we solve this problem. Okay, so what we know in region 1, we always know the Schrödinger equation. H psi equals E psi. We've also established that in region 1 and 3, the potential energy is 0. So region 1 and 3. And in region 2, the potential energy, has some constant value. Okay? But is not infinitely large. So now we can say then my Schrödinger equation in region 1 is only due to kinetic energy, right? So we've dropped the potential energy operator. Okay? And so now when I go to solve this, I want to set this up in the reduced form. So let's do that. So the way I can set this up in the reduced form is by eliminating the constants in front of the second derivative and then rearranging the whole equation to be equal to 0. So doing that, I'm just going to write psi sub x right there to make my life a little bit easier. Okay. So, and then what I want to do here is multiply through by 2m over negative h bar squared through both sides. All right. And so now that's going to be negative 2me over h bar squared times psi x. And then now I want to rearrange this so it's all equal to 0. So now I've got my second derivative in psi. I'm going to add that over to the other side, plus 2me divided by h bar squared over psi x equals 0. So now there's my standard reduced form so that I can solve this thing. And remember, in the ansatz method, right, we cry, pray, guess, solve. So hopefully you've done the crying and the praying already. Now it's time to guess. And for all these functions, we're going to guess a solution to be, sorry, I'm going to write this over here to make some more room. Our trial solution, or our guess solution rather, is going to be e to the ax, which cannot equal 0, where a is a real number. Okay? So now I got to take the first derivative of that function, and that's ax, and we know that can't equal 0, and that's part of our guess. And then the second derivative will be a squared ax. Okay? Now I can just substitute these things into my reduced form here. We know d dx squared of psi of x, so travel along over here with me. So that's a squared e to the ax. Now plus 2me over h bar squared, so I keep all of those constants. And now I know here psi of x is e to the ax, and all of this equals 0, right, from my equation there. So I can eliminate the eax, okay, because it appears in both terms. So now simplifying that, that's going to, eliminate the eax. Okay, and now what I'm left with is a squared plus 2me divided by h bar squared equals 0. And now I simply just want to solve for a using algebra. So I can see here that a is going to be negative 2me all over h bar squared, and the square root of that. Okay, and so now this means we have an imaginary root situation. And I'm going to write the solution of this as I times k, where we recognize we're going to call the collection of all of these constants k, as we know, is the wave number solution, 2me over h bar squared. Okay, so now because we know that psi of x equals eax, and we're saying a is I k, technically that's, because it was squared, we can make that plus or minus, okay? So what that means now is we can say that psi of x is going to equal we need some normalization constant A, E, I, K, X, plus some other normalization constant B, E, negative I, K, X. And so this is our classic general solution for region 1, where we know this is this EAIKX and BE negative IKX. Those describe a wave function that is a combination of sines and cosines. So it's a wave. It describes an oscillatory pattern. Okay, so I'll also write that we could write that in terms of sines and cosines, and we know either of these solutions are acceptable for the region 1. All right. So what about region